Hello students, welcome you all to the session for solutions of GATE 2023 Mechanical Engineering paper. Moving on to the very first question of strength of material subject. The effective stiffness of cantilever beam of length L and flexural rigidity EI subjected to a transverse tip load of W. A simply supported beam is given to you where the load W acting at the free end and L is the length, right? So basically, when we are talking about this kind of beam, simply supported beam with a point load at the end, A 3 EI by L cube, B 2 EI by L cube, C L cube by 2 EI, D L cube by 3 EI. Generally, what happens is the deflection delta for a cantilever beam with a point load at the end will be WL cube by 3 EI and K will be what? Stiffness, load by deflection, that is 3 EI by L cube. This will be your answer. So option A will be the appropriate right answer for the given question here. Moving on to the next question. A beam is undergoing pure bending as shown in the figure. This is the figure which is shown to you. Pure bending has been happening. The stress strain sigma and epsilon for the material is also given. The yield stress of the material is sigma y. Which of the option given represents the bending shear distribution across section AA after plastic yielding? Okay, so basically pure bending is happening and he has given you 4 diagrams here and is asking you stress distribution. Okay, basically when bending moment between the yield moments My and which you have a fully plastic moment MP, what happens? This kind of beam, when you are going to draw your curve, that is SS curve, what is going to happen? This will be a negative stress here and this will be the positive, and obviously the bending is happening at a particular region. So this is how you will be having your bending moment where SS curve will be taken. Now when bending moment may be equal or greater than your fully plastic moment, what is going to happen? For fully plastic moment, this is the condition, minus sigma y. This is sigma y. Yes or no? So obviously you can select the appropriate answer. You can select the appropriate answer. So obviously multi-choice question. Here what happens is when bending moment between yield moment and the fully plastic moment is there, this will be the curve. At that time D will be the answer. Whenever it is equal or greater than plastic moment, C will be the answer. So option C and D both are going to be an important options. Both are the right answers for the given question here in your question given to you for your plastic yielding. So option C and D will be the right answer for the given question. Moving to the next question. Which of the plots shown is or valid Mohr circle representation of the plane stress state in a material? The center of each circle is indicated by O. Right. Here what happens? There are 4 cases given to you. First case, second case, third case and fourth case, stating it as M1, M2, M3, M4. When we are talking in this first case, what's going to happen? Plane stress state where 2 stress components are there. So 2 equal and opposite stresses are there at M1. Okay, 2 equal and opposite stresses. When coming to second case, clearly Mohr circle did not cut your sigma axis, stress axis, yes or no, normal stress. there is no stress component at all. Whereas when we are talking about case 3, sigma 1 and sigma 2, where we talk about the diameter, where sigma 1 became 0, sigma 2 is the diameter of the Mohr circle. So obviously this will be something called as plane stress condition. Case 4, Mohr circle here which is given is tangential to sigma axis. So obviously one stress is going to exist which is equal to 0. So no plane stress conditions are going to come. So where you are getting your plane stress state in M1 you are getting and M3 you are getting, and here clearly if we talk M1 and M3 both will be the right answer for the given question, where A and C will be the options representing the plane stress state of the material. Option A and C will be the right answer for the given question. Moving to the next question. A beam of length L loaded in XY plane of uniformly distributed load by a concentrated tip load parallel to Z axis, resulting bending moment distribution about the Y and Z axis are denoted by My and Mz. Which one of the option given depicts qualitatively correct variations, that is moment about Y or Z along the length of the beam he is saying. So he has given the beam where the load which is been falling, and this is your X, Y and Z directions, and where P is the given point or load there, right? The options given to you are this. So students, one thing you need to understand here is asking you the correct variations of My and Mz, right? See, what is going to happen? When there is a UDL produced bending moment diagrams about your Z direction, okay, about your Z direction, what happens to the diagram? You will be having such a case where for a uniformly distributed parabolic path a negative value O, and this is M2, or you can take it as MZ you take. Okay. Now, what is going to happen when a bending moment takes about Y axis? If this is the condition, you are going to have a positive bending moment. We call it as My. So, where do you see such kind of diagrams here? Such kind of diagrams, see Y direction and your Z direction, as I stated you there. Right, so option B will be the right answer for the given question. Simple question, shear force bending moment, if you know properly, that will be your answer. Right, moving to the next question. The question here, the figure shows a thin walled open top cylinder vessel of radius R and wall thickness T. Vessel is held along the brim and contains a constant density liquid of height h. From the base, neglecting atmospheric pressure, the weight of the vessel and bending stress in the vessel walls. Which one of the plot depicts qualitatively correct dependence of magnitudes of axial wall stress of sigma 1 and circumferential wall stress of sigma 2? This is the question given to you there, right? And the diagrams are stated in this way. So before that, before going for the answer here, clearly if I see that Y is the distance, right? Let this be Y, and R is the radius given to you. This becomes H minus Y, right? I mean to say this value will become H minus Y, right? So unit weight of liquid, if you check, which is gamma. So when we are talking about weight of liquid, you will get gamma into volume, W equal to gamma into volume, pi r square h. So sigma value is what? Load by 2 pi r into T. Stress. So that is gamma pi r square h by 2 pi RT, which will be gamma R H by 2T. This will be a sigma valve value. When we comes up to pressure, Y dash, if I take a new direction, gamma into Y. Right? Now circumferential pressure sigma 2 is how much? PD by 2T. That will be gamma Y into 2R by 2T. That gives gamma RY by T. Alright? So when you plot the graph, this is your normal stress sigma 1 and this is the condition where you get gamma RH by T or gamma RH by 2T. Right? So obviously this will be stress direction, this will be Y direction. Where do you see this kind of graph where you will be having this as H by 2? Check where you will be getting this graph is. Obviously option A. Option A will be the right answer. Right? H by 2 HN. Option A will be the right answer for the given question. Right? A bit applicative part and a conceptual knowledge should be more for this kind of questions. Moving on to the next question. Cylinder bar P and Q identical lengths and radius but are composed of different linear elastic material. The Young's modulus and coefficient of thermal expansion of Q are twice the corresponding values of P. Assuming the bars to be perfectly bonded at an interface and their weights to be negligible, the bars are held between the rigid supports as shown in the figure, and the temperature is raised by delta T. Assume the stress in the bar, which is homogeneous and uniaxial. Denote the magnitude of stress in P and Q, sigma 1, sigma 2 respectively. What of the statement are wrong? That is, P and Q, two bars with stresses sigma 1 and sigma 2. Interference between P and Q moves to the left after heating. The interference between P and Q moves to right after heating. C, sigma 1 less than sigma 2, D, sigma 1 equal to sigma 2. So basically what happens is, let this be length L1, let this be length L2. So obviously can I write L1 and L2 which will be equal to beta into L? So when you draw a diagram here with the two different conditions, sigma 1, sigma 2, P and pressure acting here, sigma 1 is P by A, sigma 2 is P by A, that is force per area. When both the area of cross sections are same, what's going to happen with thermal stresses? P equal to L alpha delta T, that is your deformation, right? Minus PL by AE. Let it be delta suffix P. Deformation of Q. Two alpha L into delta T, right? Minus PL by AE, which will be delta Q. So obviously which one is greater and which one is lesser, my here? Clearly delta Q is greater than delta P, right? So obviously what happens to the given answer here? The interface between P and Q, what happens? It is going to move towards left after heating. That will be one wrong answer. I mean, he's asking you statements are correct. That will be once. And one more thing is sigma 1 will be equal to sigma 2. That is A and D will be the right answers for the given questions here. Got it? Moving to the next question. A cylinder of bar length of 5 meters, cross section of 10 meter per second square. The bar is made up of linear elastic material with density 2700 kg per meter cube. Young's modulus 70 gigapascal. Bar is suspended as shown in the figure at a state of uniaxial tension due to self weight. Elastic strain energy stored in the bar equal to dash joules, and acceleration due to gravity is 9.8 meter per second square. So given L equal to 5 meters, A equal to 10 meters square, density as 2700 kg per meter cube, Young's modulus as 70 gigapascal. So the energy will be U is equal to 0 to L T square dx by 2AE, which will be load W by L into X whole square dx by 2AE, which will be equal to W square L cube by L square 6AE. That will be W square. How can I write my W square, or I'll write it as gamma equal to W by volume, that is A into L. At that time this will be gamma square L cube A by 6E. So weight of the bar W equal to rho GV, right? So gamma equal to rho GV by AL. Gamma equal to volume gets cancelled, rho G. So V equal to, substitute back, rho G into rho G square L cube A by 6E. From there 2700 into 9.8 whole cube, because square into rho G. Length 5, area 10 by 6 into E, 70 into 10 power 9. Calculate the volume. Strain energy, how much you are going to get? 2.08 joules. This is regarding the strain energy which you are going to get. Right? Moving to the next question. The cylinder transmission shaft of length 1.5 meter, diameter 100 mm is made of linear elastic material with a shear modulus of 80 gigapascal. While operating at 500 rpm, the angle of twist across its length is found to be 0.5 degree. Power transmitted by the shaft at this speed is dash kilowatt. This is a cylindrical shaft, let it be, which is rotating, right? The length is given as 1.5 meter, diameter as 100 mm, which will be 0.1 meter, G as 80 gigapascal, N 500 rpm, angle of twist theta is 0.5 degree, which will be 0.5 into pi by 180, which will be radians. We all know T by J is equal to G theta by L, right? Torsion equation, T by J equal to tau by R equal to G theta by L. And also for J is pi d power 4 by 32, right? Substitute T equal to G 80 into 10 power 9 into 0.5 into pi by 180 into pi by 32 into d power 4, 0.1 power 4 by nothing. This is G, this is theta, this is J by L. Length is 1.5. So what will be the value of T? On substitution, you should get value of T as 4.56 into 10 cube Newton meter. Right? So power is torque into omega 2 pi n by 60 into T, which will be 4.56 into 10 cube into 2 pi into 500 by 60. You should get a power of 238.6 kilowatt. This is your power. That is what is asking you. the power transmitted by the shaft with the speed of 238.6 kilowatt. By this, we have completed the questions of strength of material subject from mechanical engineering paper of GATE 2023. Hope every solution is clear to you. Thank you, students.